Hello everyone and welcome to the first lecture of this course where we are going to learn how to analyze and design different types of slab systems. Now in this lecture, is going to be an introductory lecture about all the different types of slab systems. So basically we are going to discuss the workflow that we are going to use and we are going to start with discussing the first type of slab system that we are going to work with, the advantages, disadvantages, and some design considerations. So first of all, let's start with the workflow that we follow when we are designing any building. So what do we usually do when we want to design a building? So the first step is we go to SAFE and we design for our slab system. It doesn't matter what slab system that you are going to use, but we have to design for it. We need to check for the serviceability conditions and check the reinforcement that is required. So this is the first step, and this is what we are going to learn in this course now. So the next step is we move to ETABS and we design for our vertical elements, our shear walls, our columns, and our beams if they were a part of our lateral force resisting system. So after we're done with designing for our vertical elements, we are going to export the data that we have back to SAFE in order to design for our foundation system. So these are the three steps that we follow in order to design any structure that we have. Now, SAFE is usually used for conventional reinforced concrete slabs, which are solid slabs, flat slabs, composite slabs, hollow block slabs. These are our typical conventional reinforced concrete slabs. Now, in case of post-tension slabs, we usually go for a dot builder, and in case of deck slabs, which is a slab that is supported on steel beams, we go for ETABS because deck slabs are not supported in a CSI SAFE. Now, before we go into our software and we start with designing or preparing our model, we need to go for some preliminary steps, which are or which is preparing our plan in order to import it to our software. So what we do is we have our architectural plan that is prepared by our architect in or using AutoCAD. We are going to take this architecture plan and we are going to convert it into a structure plan. And when we say structure plan, our structure plan includes the structural elements that are of interest to us. Only, nothing else. We are going to remove everything and we are going to keep the structural elements that are important to us. This is the first step that we go for. Now, the second step is that we are going to convert this structure plan into an analytical plan. And we are going to talk more about analytical plan later on in this lecture. Now, the main load that we have when we are working is in AutoCAD. 70% of our work is related to AutoCAD because the more or the better the preparation that you have through AutoCAD, the easier your work is going to be when you move on to your software, whichever software it is, whether it was CSI SAFE or ETABS, etc. So the more accurate your design is or your plan is using AutoCAD, the more time you input into um, preparing your plan using AutoCAD, the more or the easier your work is using SAFE. And you are going to see how when we start working with in our next lecture. Now, usually with practice, you are going to become well acquainted with the steps that you need to follow, and it's going to take you between 40 to 60 minutes in order to prepare your model. Now, why do we have to start with slabs? The first reason is the behavior. So first, we need to select the type of slab, uh, whether it was a flat slab, a solid slab, any type of slab that we need to use. We cannot assume the type of slab that we need to use So because let's say that I took into assumption that I want to use a solid slab for this structure. And later on, when I'm working or in later stages, I noticed that a solid slab does not work for this type of structure. So I have to go back and I have to repeat my work, and this is not really convenient. So we need to know the type of slab that we need to use. Now, the second reason is weight. Now, the weight of, or basically, we need to make sure that we have the right slab selected in terms of weight, because when we're moving into design for our vertical elements, if we notice that uh, the thickness that we have, for example, for our slab is not efficient to design our vertical elements, again, we have to go back and we have to repeat our work, and this is not convenient again. So this is why putting in effort and putting in the time while preparing or while designing for our slabs is very important, so that uh, we do not go through any issues in the later stages of designing our structure. Now, when it comes to the slab type selection, selection depends on different criteria. The first one is the occupancy. So what is this building for? What is this structure that we are building? What is it going to be used for? So is it going to be a residential building, a storage, a parking, etc.? This occupancy, when you determine the occupancy of your building, this in turn determines the loads that are going to be applied on your structure, or you can have a better image of the loads that are going to be applied. This way, you have better information in terms of selecting the type of slab that you want to use. Now, the second criteria is the span, and the span is very important because the span is directly related to deflection, and deflection is one of the criteria that we check for when we are checking for our serviceability conditions, and this deflection should be within an acceptable value. And if the span of my slab, or the span from one column to the other, is big, this means that we require a higher thickness. So this is why it's very important to know the spans that we have in order to know the thickness that we need. This way we know the type of slab that we need to use, because every type of slab has a different thickness. Now, the construction time. Usually nowadays, 1/3 of the projects being constructed go for post-tension slab systems. Why? Because usually when you go for conventional reinforced concrete slab systems, it requires you between 14 to 21 days in order to remove the formwork. Whereas for a post-tension slab system, first of all, it requires less labor, and second, it you can remove 50% of the formwork right after 7 days only, and this will save you so much time. However, this does not mean that we do not use reinforced or conventional reinforced concrete systems. Now, the final criteria is architectural constraints, and it depends on the architectural design that you have in front of you. This plays a role in the type of slab system that you are going to use. Now, the different types of slab systems that we have are solid slab, hollow block slab, waffle, flat slab, composite slab, and hollow core slab. Now, the slab systems that we are going to cover in this course are solid slabs, hollow block slabs, flat slabs, and composite slabs, and we are going to discuss each and every one in details in future lectures. Now, when it comes to the structure components, we already discussed that we need to prepare a structure plan, and in this structure plan, we need to include only the structure elements that are of interest to us. Now, what are these structural elements? The structural elements are as follows. You have your beams, whether it was a drop beam or embedded beam. You have your slab, which usually in our AutoCAD plan, we put it as our slab limit. We have our walls, whether it was a shear wall or a retaining wall. We have our columns and we have our partition walls, which are very important because it helps us determine the location of our beams, because our beams are usually embedded within our partition walls. Now we are going to start talking about or discussing the first type of slab system that we have, which is our solid slab system. Now, this is the first slab system that we are going to analyze and design, and we are going to start with that in our next lecture. However, let's discuss the concept of a solid slab system in this lecture before we start working with AutoCAD and CSI SAFE. So, solid slabs is usually used for buildings and bridges. It is for every panel that you have, every panel within a solid slab should have four sides and each side should have a drop beam. Just like here, this is one panel and this panel has a drop beam from every side, and this drop beam, the span of this drop beam or the cost effective span should not exceed 5 meters, which means that the total area of this panel should not exceed 25 meters squared. Why? Because this helps us reduce the thickness of our slab system. Now, this is the main difference between a solid slab and our flat slab, which is this span that we have here because we are using less thickness. Now, usually when we design for a 1 meter strip, and the remainder of the slab is a typical reinforcement of this 1 meter strip that we design. Usually we go for a minimum slab thickness of 8 centimeters in case of static load, 12 centimeters in case of dynamic loads or vibration. So let's say, for example, you have a car. This is what we consider as a dynamic load. Now, practically, we do not go for 8 centimeter thickness. We start from 12, but it can usually be used. However, it's not really advisable. Now, the practical considerations that we are going to go for, first of all, is our slab thickness. So I'm just going to explain briefly the steps that we are going to follow when we start with our design, whether it was a solid slab system or any different type of slab system. So what we do, first of all, we determine our slab thickness. We start, as I said, a practical consideration is going to be starting 12 centimeters to 16 centimeters. Now, if we reach an 18 centimeter thickness, this means that we are going to go for a flat slab system. It's no longer a solid slab system. So we determine our slab thickness, then we check for our deflection. Is our deflection good? If yes, then great. We move on to our reinforcement. If not, then we need to change the thickness. Now, we also check for punching shear usually, and this depends on the type of slab that we are going to use. Now, when we are working with a solid slab system, we have one layer of reinforcement. As I said before, if we go for an 18 centimeter thickness, we now have a flat slab system. We require 2 layers instead of 1 layer. So we have 1 layer of reinforcement bottom. Now we need to know the reinforcement that is going to be used. So what we do is we start with a 6 phi 10 millimeter diameter bar. If it was okay, then great, we're done. If not, we move on to a 5 phi 12 bar size. Again, if it's okay, that's great. If it's not, then we move on to a 6 phi 12 bar. If it's not okay, we go back to our slab thickness. We increase our slab thickness from 12 to 14 centimeters, and we repeat our steps. So this is basically the steps we are going to follow, and you are going to understand it a bit more or much more when we actually start performing these steps. Now we are going to discuss the concept of drop beams. Now drop beams, you have different dimensions within your drop beam, which is your edge or the depth of your drop beam, which is basically the thickness of your slab added to the drop thickness, which is, or the drop depth, which is H2. And you have the minimum width B, which is equals the width of your partition wall. Now, in order to determine H2, we need to find our depth, H. Now, H is the max of either 50 centimeters or 2 to 3 times slab thickness. So let's say, for example, we have a slab thickness of 12 centimeters. 12 times 2 is 24. 12 times 3 is 36. They're both less than 50, so our starting depth H is 50 centimeters. So our H2 is 50 minus the thickness of our slab, which is 12, which gives us an H2 of 38. This is basically when we are talking about the dimensions of my drop beam. Now, the location of drop beams, they're usually located within partition walls. They're embedded within partition walls. Now, in case we cannot place a drop beam at a partition wall location, then we have to support this wall using an embedded beam to reduce the excessive deflection. Why do we have excessive deflection at this location? Because the weight of our wall is too big. It's between 700 to 1000 kilograms per linear meter, and we do not want this load to be applied directly on our slab system, so we require an embedded beam to carry this load for us. Now, the advantages and disadvantages of our solid slab. Now, we said that our solid slab is going to have less weight because we are using smaller thickness. So, usually the thickness that we use is between 12 centimeters to 16 centimeters, and this is an advantage for us because the smaller the thickness, the more feasible your project is going to be. Now, it is also the best choice for large projects, and especially if you have a typical architectural design that is not really complicated, we always resort for solid slab systems. For example, a student apartment that does not have these complicated architectural design concepts, then we go for a solid slab system as it is the best choice usually for us to go for. Now, one main disadvantage is that it is a permanent obstacle for architectural purposes. So let's say you come in, you want to change the layout of your house. So you want to remove a wall. What you're going to see is you're going to see that you have an embedded beam within this wall. This is what we call a permanent obstacle. So this kind of restricts us in terms of the architectural design that we want to go for, or any architectural modifications that we want to go for later on. And this is one of the main disadvantages of a solid slab system. Now, we are going to move on to the concept of an analytical plan. Now, we said before that we need to convert our structural plan into an analytical plan, and this analytical plan is what we are going to import or into our software in order to start with the design of our model. Now, an analytical plan is converting a physical model, which is a volumetric model, into a finite element model, basically 1D and 2D. So we have two types of elements here, which are frame elements and area elements or shell elements. So our columns and beams are usually frame elements, which are 1D elements. Our shear walls and slabs are area elements or shell elements, so they are 2D. Now, how do we draw these in AutoCAD? So for a frame element or a 1D element, we have three dimensions, okay? We have small h, b, and big H here. So we can see that the small h and b are similar in dimension. They're close to one another. So what we do is, in AutoCAD, we draw our h, our big H, and using our software, we will define our B and our H, our small h. Same for our beam. In our beam, we are going to draw our L. And using our software, we are going to define our small h and our B. Now, a column, usually what we do is we define it as a point. So in AutoCAD, we draw it as a point that is represented by its CG. And then Using CSI SAFE, we will define the B and the H. We will say, for example, it has dimensions of 25 by 25, let's say, using SAFE. But in AutoCAD, for our columns, we are going to draw a point that represents the column CG, and we are going to draw a line for our beam, which represents the beams L. Now, for an area element, what we do is, it's kind of the opposite of what we do in a 1D, 1D model. We have our length and our height that are close or similar in dimensions. So what we do is that we draw them, and using SAFE or using our software, we will define our thickness. So this is how we approach 2D elements. Now, finally, the last point that we are going to discuss here is our wall, the dimensions of our wall. So usually the length of our wall should not be less than 5 times the thickness. So the thickness is usually, minimum thickness is 25 centimeters. So the length is 5 times 25, so the minimum length that we go for is 1.25. So we have a minimum length of 1.25 and a minimum thickness of 25 or 125 centimeters and a minimum thickness of 25 centimeters. These are the preliminary dimensions, or the dimensions that we can start with for our wall, or shear walls usually. So these are basically the concepts that we need to know before we start with applying, or we start with performing our analysis and design for our slab systems. So again, the first step that we are going to go for is we are going to go to AutoCAD. We are going to have an architecture plan. We are going to convert it into a structure plan, then into an analytical plan. Then we are going to go to SAFE. We are going to prepare our model and check for our serviceability conditions, and then check for the reinforcement that is required. So in our next lecture, we are going to start with the first step, which is preparing our AutoCAD plan. We are going to start with our next lecture with converting our analytical or our architecture plan into a structure plan as a first step. So I'll see you in our next lecture.